So today, let me do this other approach, which are the backward equations. We've looked at the forward equations, the forward master equation and the forward Fokker-Planck equation and so on. But we said that that they were called forward because there is an alternative approach, which is the backward approach. Right, and the idea being that what we wanted to write down was the time evolution of these probabilities that right. So we wanted to write down the time evolution of these probabilities. You start from some initial state psi naught and you go to some state psi after some time t has elapsed, and how do these probabilities evolve in time. So the way we had done the forward was to say that well, there are two states involved here, the initial state and the final state. And then when we were thinking about the forward equation, we had written something like this, right? Psi naught was, we looked at just the step before the final step. So before the final location, so essentially the final step. So we integrated out over all psi prime t psi naught, and then right. Actually, this is in terms of probability. Delta t, right. So we said that how do I get to this final state psi? I somehow have come to this state psi prime starting from this initial position, and then for this final step, I in this delta t amount of time, I go from this psi prime to this desired state psi, and then I integrate out over all psi primes, right? And that gave me my master equation. So this was integral over all psi primes, right? P of psi prime t psi naught, the transition probability to go from psi prime to psi. So this was my incoming terms, and then I had my outgoing terms, which was that I was at psi t psi naught, and I transitioned out of that to any other possible state, right? Integrated out over all possible states. So this was my forward equation. Starting from here, we had Taylor expanded these probabilities, we converted into rates, and then we got a forward master equation. So we'll do exactly the same thing, but now we'll try to look about the initial step instead of the final step to reach the desired state. We'll look about expansions about this initial state psi naught, okay, and that will give us our backward equation. So that's the idea. So again, it's the same quantity that I'm looking at. So let me do it here. So P of psi t psi naught. Let me explicitly put a t naught, this initial time doesn't matter. And then I consider transitions out of this initial state to some other intermediate state, psi prime. Okay. All right. So let us say that I have transitioned to a state psi prime in time t naught plus delta t, starting from state psi naught at time t naught. Okay. And then from this intermediate state, I will go to whatever final state that I want. So, I will go to P of psi comma t starting at this intermediate state psi prime at t naught plus dt, right, delta t. And I will integrate out over all possible intermediate states. Okay. So, that is one part in that where I say that in this interval of time delta t, I have transitioned to some state psi prime, and then in that remaining time whatever is left I have to go to this final state psi. And then the remainder is that in that time I did not make any transitions, which is 1 minus integral d psi prime p psi prime t naught plus delta t psi naught comma t naught, right. So, this is the probability, total probability that I have made a transition out of this state psi naught to any other state in this interval of time delta t, and 1 minus that therefore is the probability that I have stayed at this state psi naught. So, then in the remaining time I have to go to my final state psi comma t starting from that initial state because I have not moved out of it, t naught plus delta t. Is this clear? So, this term, so I was at psi naught at time t naught. In an interval of time delta t, if I have gone to any other state psi prime integrated over all states, this is the total probability that I have moved out of psi naught, and 1 minus this is the probability therefore that I have stayed at psi naught after this time delta t. So, that if I have stayed at psi naught, now then the probability that I should look at is that I go to psi naught from psi naught to psi because I have stayed at psi naught, except my time is now no longer from t naught, but t naught plus delta t because delta t time has already elapsed. Okay. So, this says that I go in this time I go to some new state, and then from that new state I go to the final state. This says that I stay at psi naught in this time delta t, and then from that psi naught I go to my desired final state. Yes, okay. This is the root sort of equation, everything else is mathematics. So, this is fine. Fine. All right. So, now we will do the same thing that we will, what had we done. So, we will write down these transition probabilities in terms of transition rates. So, let me say that we will write down probabilities like this, so that probability that I go to psi prime at some time, let us say t naught plus dt starting from some psi. So, this term essentially psi naught at time t naught. Okay. I write as the transition rate omega from psi naught to psi prime. So, into dt, right, in the limit that dt tends to 0, right. So, these transition probabilities I write as rate, transition rates times the dt in time interval. So, from the initial state psi naught to the final state psi prime. So, psi naught is exactly like we had done in the forward case. So, the same definition, I am just rewriting this again. But now what I will do is that of course, I will substitute this into these equations and therefore, write this equation in terms of the transition rates. So, this is exactly what I have written down over here, right, omega psi naught to psi prime dt. So, let me just write that omega psi naught to psi prime into dt, right, and the same over here. This is again the same thing psi naught to psi prime in this interval of time dt. all right. Now what I will do is that I will next assume stationarity. So, which essentially says that what is important is the intervals between times. Remember, we had talked about stationary Markov processes, where it involves differences between time, but not the absolute values of the time. So, by doing that, what I will do is that I will shift this dt to this side. Okay. So, it was t naught plus dt to t. What I will say that this is, let it remain t naught, and this I will call as t minus dt. Okay. So, that is stationarity. And same here. This is t naught, this is t minus dt. Okay. So, that is that plus stationarity. So, plus stationarity. Now, what I will do is that now I will Taylor expand these probabilities. I have p of psi t minus dt, p of psi t minus dt. I will Taylor expand these probabilities, keep terms up to lowest order. Let me keep the forward equation so that we can contrast later. Yes. Here, this equation, yes, okay. Naught plus dt to t. That is the stationarity assumption, right? So, I was, here is my time axis. So, I was at t naught, this is t naught, this is t naught plus dt, this is t, and this is t minus dt, right. So, earlier it was t naught plus dt to t, this interval. Now, I am saying from t naught to t minus dt. So, this interval. So, just shifted everything around by this time dt, the absolute times, but the gap between these two events stays at the exact same value, right. So, that is the stationarity assumption, that only time intervals matter, the precise values of the exact time values do not matter, right. Okay. So, with that assumption then let me now do this Taylor expansion. So, p of psi t, p of psi t psi naught t naught is integral d psi prime omega of psi naught to psi prime, then this probability. So, p psi t psi prime t naught, right, minus, so this Taylor expansion. So, minus dt del del t of this quantity p psi t psi prime t naught, okay, first order term. And then again similarly for this, plus 1 minus integral d psi prime d psi prime omega of psi prime to psi naught, right, and then again the same thing, p of psi comma t psi p of psi comma. So, what did I have here? I had t naught and t minus dt, p of psi naught minus, right, minus dt del del t of p of psi t psi naught, right, comma t naught. What there is? There is a dt. Yes, there is a dt. dt, right? Thank you. Okay. I want a derivative of p of psi t. So, I'll only of course, all right. So, p psi t psi naught t naught. I have a p psi t psi naught t naught over here, right. So, this cancels with this term over here, and so what I am left with is I will keep only terms up to order dt. So, I have this term del p psi t psi naught t naught del t, that is this term. Okay. So, this into this one over here is this term. I have taken it on the other side, and then the other terms that I have left are integral d psi prime p psi t psi prime t naught omega have I written this correctly? Was it psi prime psi naught? Psi naught to psi prime. Yeah, that is fine, right? Because it is at psi prime, it has to go to fine. Omega psi prime psi naught. Omega psi prime psi naught. And this term is of order dt square, so it doesn't matter. And then the only term I have left with is this minus p psi t psi naught t naught integral d psi prime omega of psi naught to psi prime to psi naught. I hope I have this correct. Psi prime to psi, omega psi naught to psi prime, and then omega psi naught to psi prime. Yes, so this is fine. Right. Okay, so this is the backward master. So this is the backward master. Right, so you're integrating out over all intermediate states, psi naught to psi prime in the first step, and then from psi prime to the final state. And this term corresponds to the probability that you had not transitioned out of this initial state, and therefore you go from the initial state to the final state in that time. Okay. So here, unlike in the forward case, so this was my forward, I don't have a straightforward gain term and a loss term essentially, where I come into psi and then I go out of psi. But here I have to interpret it in terms of this initial state, that this term is in the first step I had gone to some intermediate state, and this term is in the first step I had stayed at wherever I was, and then I make the transition. Okay. So both of these are essentially describing the same physical process. It's just two ways of looking at this time evolution, one by considering the final state and another by considering the initial state. Is this part clear? It has certain advantages. Mostly people look at forward equations. Backward equations are especially useful when you want to look at times of processes. That okay, how long did it take for this process to happen? And there it is the backward equations that are actually useful, or more convenient rather. The backward equations are more convenient, and I'll show why. Okay. All right. But this is the master equation. From here, the next what I'll do is that I'll derive the Fokker-Planck equation. Again, exactly the same way that we had done. How had we done from the forward? We had just these transition probabilities. We had written in terms of the initial state and then the size of the jump. and then we had Taylor expanded in the size of the jump, kept only the first two terms, that gave us our Fokker-Planck equation. So, we will do exactly the same. We will take the backward master, rewrite these transition rates in terms of the jump size, and then keep only the first few terms, and that will give us our backward Fokker-Planck. And you will see one of the advantages of the backward Fokker-Planck as compared to the forward Fokker-Planck. So, what we had written was this, that if I have these transition probabilities psi naught to psi prime, I would write them as functions of the initial state. So, in this case psi naught, and then the jump size, right, delta xi. So, if I do that, then what I want to do is I want to integrate out over all jump sizes now. So, d of delta xi, okay. This I will write. So, essentially in this format, in over here, my psi prime is psi naught plus delta xi, right, initial plus size of the jump. So, I will just rewrite over here, this small w becomes capital W, initial state, jump size. This xi prime becomes xi naught plus jump size, right. Here I have again W xi naught jump size. Okay. So, again what I will do is that I will now do a Taylor series expansion of this in terms of delta xi. So, the first term note will give me p xi t xi naught t naught, right, multiplied by this, which is exactly this p xi t xi naught t naught multiplied by this transition rate. So, the first term will cancel this first term, or I will be left with other higher order terms. So, then if I want to write the higher order terms, yes, yes, where here, here, yes, 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 of course, d of delta z. So, then what I have on the left hand side is del p del t of xi t from xi naught t naught is equal to all of these terms. So, summation of n equal to 1 to infinity, right. I have an integral over d delta xi, right. I have that thing which is whatever w of xi naught delta xi, right, and then I have a delta xi to the power of n, and then del xi naught to the power of n of this probability p xi t xi naught t naught, right. I've just expanded out that out in Taylor series. So, this is like exactly what I had done for my forward master equation to get to the Fokker-Planck. Okay. Okay. And then what we will do is that we will just keep the first couple of terms. We will just keep the first couple of terms p psi naught delta psi, all right, del xi naught. So, let me think about the first term. So, the first term is just this d delta xi w times delta xi to the power of 1, then del xi naught of this. So, let me call this a1 of xi naught, then del psi naught of p xi t xi naught t naught, right? And then there is A2 of xi naught del 2 del xi naught 2 of p xi t xi naught. Okay. Half, right? So half. This is essentially n factorial. I missed that. Sorry. Where my A1 and A2 are again exactly the jump size moments. So my A1 is A1 of xi naught is integral d delta xi w of xi naught delta xi times delta xi, right? And A2 of xi naught. All right. So again, these are the moments of the jump distribution, except these are now calculated using the transition rates from the initial state, which is xi naught. When we were calculating the moments of the jump distribution in the forward A, we were calculating using the final state. Here it is from the initial state psi, and that gives me that gives us our backward Fokker-Planck. So del P del T of psi t xi naught t naught. This is my backward FP. Now, one of the advantages, hopefully, if you see, if you remember the forward Fokker-Planck, right, it had a very similar structure, of course. So now these variations are with respect to the initial state. There, the variations was with respect to the final state. But there, if you remember the del xi that we had written, it was del psi of A1 times P and del 2 del xi 2 of A2 times P, right? Here, these coefficients have come outside this derivative, and that makes life simpler in certain contexts. So that's the property that allows us to describe these times using the backward equations more conveniently than the forward equations. So these integrals that I have, these moments, these are just over delta xi. Delta xi does not appear here, so those just stay. So I can just do that integral independently of that, and then I get these moments times the derivatives. Okay. This all of this might look a little complex, but once we work out a few examples using these forward versus the backward, hopefully things will become clearer. But at least hopefully you appreciate that in the forward equations, we are doing things with respect to this final state. In this backward equations, we are doing things with respect to this initial state psi naught, the first step out of this equation. All right, so this was my backward master equation. Is this clear? So then I'll move to times essentially. So we will work out. So for example, therefore, if you for the master equation, for the random walk, what is your A1 and A2, your jump size distribution, For the backward master equation. So what is the question? So you can, of course, what are your transition rates out of these initial sites, right? So you with rate whatever P and P, if it's a symmetric random walk, or P and Q, you transition out of these initial state, whatever is the initial position x naught. So, for example, here if you were to write down the backward equation, just this would just give you d, right, for example. So, d times del 2, so if I am writing my backward equation, del p x t starting from some x naught t naught del t is just d times del 2 del x naught square of this quantity. Okay. And similarly over here as well. So, we will do that, we will do that. Yes. Yes. How do you mean we are coupling them? Hmm. We have a series of different. So, my initial condition is the same, of course, that I am starting from this state and going to this state. We are fixing the final. So, I have ultimately I am looking at this probability, right? P of psi t given psi naught t naught, right? And I am asking how does this change with time? But the quantity that I am looking at is this in both the cases, both the forward and the backward. Then the way I look at it is different in these cases, but my initial condition in both of these cases is this, that I start from psi naught t naught and I have to reach the state psi after some time t has elapsed. Uh, what do you mean I'm mixing, for example, initial conditions? Here, yes. Okay, so but again, so here is my state. I was at psi naught, I want to go to psi. That is the process that I'm interested in. How I do is that in the forward case, I say I have arrived at psi minus d psi, however I have, and then I'm looking at this evolution. Here I am doing psi naught to psi naught plus d psi naught in this initial time, and then I'm going to this final state. But regardless of whether I do this and then a big jump or a big jump and then the final state, my process that I'm looking at is psi naught to psi. That does not change in either the forward or the backward. Right. So, it is the evolution of that same probability for that same process described in two ways, depending on whether you are doing an expansion about this first step or doing an expansion about this last step. That is all. All right. So, then we will pivot to talk about times and see how this formalism applies to times. Maybe I will do a simple thing today, and then I want to keep this somewhere. So, I'll keep the Fokker-Planck and the master equation over on this side, and then just so del p psi t psi naught t naught del t is d psi prime integral over d psi prime p of psi t psi prime t naught omega of psi naught to psi prime minus p psi t psi naught t naught omega of psi naught to psi prime. So, this was my master equation. Note that in the forward master equation, when I was writing down these rates, it was psi to psi prime in one case and psi prime to psi in the other case. Here in both of this, it's the same thing, psi naught to psi prime, psi naught to psi prime. Okay. Is that because of the probability in front of this is different in the two terms, the interpretation is different of what is happening. Anyway, so passage times. Passage. First passage times. So, often when we are talking about stochastic processes and So I start from some state psi naught at some time t naught, and I want to look at some final state psi final. I want to ask that when does this stochastic process essentially reach this state for the first time. So, let me call this some t. So, essentially what I want to look at is the distribution of these time intervals t minus t naught. So, distribution of these time intervals where it reaches this state for the first time. Okay. And this is often, of course, it's generally important, but often again in biological context, for example, I don't know, let's say you have a protein, which is, we were talking about target search on DNA. So you have a protein which is diffusing along a DNA, and it needs to find some site. So here is my protein which is diffusing. It needs to find some target site. So I want to know when it reaches this target site for the first time. When it reaches, maybe some reaction happens. Right? Some gene gets expressed, some other protein gets produced. Or for example, when we are talking about this E. coli that was moving in chemoreceptors, sorry, in a chemical gradient, these chemical molecules were diffusing, and they get absorbed by the receptors. So we're thinking of that in terms of a diffusion process, but we would ask equivalently this time question, that how long does it take for this signaling molecule to get absorbed? And once it gets absorbed, it triggers a cascade of changes. The bacteria E. coli maybe swims in one way versus the other way, and so on. Okay. So it's not just, so essentially we want to know the first time that this process happens. So that's why it's called the first passage. Okay. The first passage. And this distribution of times, so I will write as this quantity. So f of tau, right? F of tau to reach a final state from a given initial state, xi naught. Okay, so what is this distribution of times? So just before we do, so that's the thing that we'll try to work out maybe next day, but before we do, the first thing to notice is that this is not the same as, so it is, so for example, I have some probability to be at psi f, let's say after time tau has evolved from when I was in the initial state, right? So this is the sort of probability that we were looking at. I start at my initial state at some time, t naught, whatever, 0, and I go to this final state psi f after some time, t naught plus tau or 0 plus tau. This is not, so it is, this first passage time is not some scaled down version, let me say some alpha of this. Okay. These two are very distinct quantities, because this probability, the probability that you were at psi f after some time tau has evolved, let's say has this trajectory, but it also has this trajectory and then this trajectory. So you were here and then you come back here after some time. So you can make multiple visits, right, to this same state. So this probability that you were at psi f after some time tau is distinct from this probability distribution of times when you visited this site psi f for the first time. Okay. So these are two distinct things. That is the first thing. And essentially, of course, this, but anyway, this has to be less than or equal to this probability. All right. So we'll find out, we will sort of derive the equation for this distribution of times, and we'll show that it obeys the backward equation as well. But before we do that, let us do this for the simple random walk process, so that we can always cross check our more formal results. All right. So I have this distribution of times f of tau to reach the final state starting from the initial state. Now, often, of course, if one can get this full distribution, it is of course nice, but often it's enough to talk about what is the average time does this process take. So what is the mean first passage time? Okay. So essentially, often one will talk of mean mean first passage times, and the mean first passage time, for example, average tau is nothing but this distribution times tau integrated over all times from 0 to infinity. Right? This is just my mean first passage time. So, for this random walk case, let me, without doing the theory first, let me just write down an equation for the mean first passage time. So, remember, here is my standard random walk. I am at some site. I can hop to the right or to the left. Let's say I do the symmetric version with probability half and half, right? And each of these steps takes some time tau. Okay? So I stay. My residence time in any of these sites is tau. And I want to ask that what is the mean time it takes me. So, for example, so this is my random walk, and let's say I am in this domain, so of 0 to L. Let us say both these boundaries are absorbing, for example, and I can ask that how long does it take before I get absorbed at one of the boundaries. Okay. So, these are my final states essentially, or I could have other boundary conditions. I could have this as reflecting and that as absorbing, and then one could ask how long does it take to get absorbed at this boundary. But I want to write down this equation for this mean time. So, essentially what I want to write down is an equation for this mean time. Okay. If I were starting from some site x. So, this is my site x, this is x plus a, this is x minus a, and so on and so forth. Is this setup clear? The first time the particle reaches from? Correct. Reach there for the first time. So, essentially let us say this is where I am starting out from. Let me call, since it's the initial position, let me call it x naught. Okay. So, my random walker starts from some initial position x naught. What is the first time it reaches one of these boundaries? Let us say that is the question that I am interested in. Okay. So, here my psi f is this 0 and L, and my psi naught is this starting position x naught. So, I want to write this mean time, and again I will do this exactly like I had done for the probabilities. So, if I am at some position x naught, this is my initial position. The first step out of this position I can take in two ways. I can either go to the left or I can go to the right, right, each with a probability half, and this step takes some time. I've called everything tau. Let me call it delta t. Okay. This step takes some time delta t, and at the end of that step, with probability half, I am at the site x naught plus a, right, and with probability half, I am at the site x naught minus a, right. Once I am at the site x naught plus a, it takes me some mean time tau of x naught plus a to reach again the whatever boundaries condition that I have set, or if I am at x naught minus a, it takes me this time tau of x naught minus a. So, I write down a recursion relation for these mean times. Is this clear? With probability half, I go to the right or to the left. Once I am at the right or left, the time it takes is tau of that position. So, it is now a new process where I am starting from x naught plus a, and I ask what is the time it takes. And to go from x naught to either of these steps, it has taken me a time delta t. It is the time it takes me to escape from some site. So, every delta t time, remember in my discrete time, discrete space random walk, every time delta t, I take a step either to the left or to the right. Let me subtract this from both. This is fine. This recursion relation, you understand. So, let me subtract this thing from both sides. Tau of x naught minus tau of x naught is equal to delta t plus half tau of x naught plus a minus tau of x naught plus half tau of x naught minus a minus tau of x naught. So then this left side is of course 0. So I divide by a, divide by a, and this thing is what? So this is now the first derivative minus another first derivative. So this is the second derivative in the right. So then what I get is so if I divide by a once more, no, this is fine. Okay, so that was my definition. So I have del 2 rather del 2 del x naught square of this mean time tau of x naught, that is from here, that plus 2 delta t by a square is equal to 0, right. So to get the second derivative, I divide by a once more. So that gives me a square here, and then this 2 if I bring to this side. So that is 2 delta t by a square over here. Huh? So right now I will look at the boundary conditions. Right now I'm just looking at the bulk equations. When we solve it, of course, we'll have to put in the boundary conditions correctly. All right. Now this is of course done in the limit that a goes to 0, since I'm writing down this del x naught. So a goes to 0, delta t goes to 0. What is this term? A square by 2 delta t d, right? So what this is nothing but, for the diffusion equation, is 1 by d. So del 2 del x naught square of the mean first passage time starting from this state x naught goes as is equal to minus 1 over d. So this is the mean f first passage time, MFPT. Mostly people talk about MFPTs, but mean times, but you can of course look at higher orders as well. Now, of course, to solve this, you need to put in the correct boundary conditions. What is the boundary condition that you want to solve? So, for example, if you say that it's either of these boundaries, 0 and L, and then both of these boundaries are absorbing, which means that if you started off from 0 or if you started off from L, then your mean times would of course be 0, right? If you're starting off from the absorbing side. So you can solve this equation with subject to these boundary conditions, and so tau of x naught would be 1 by 2d, 1 by 2d Lx minus x squared. Okay, so if you solve this equation subject to these boundary conditions, your tau of x naught would be Lx naught minus x naught square, which means that if you are plotting this mean time tau of x naught as a function of your x naught, your starting position. So of course 0 to L, so 0 to L. Your maximum time is when x naught is L by 2. So your curve looks something like this, and this value is so L square by 2 minus L square by 4. So L square by 8d. At x naught. And indeed, roughly that is what you would expect. So if you had a random walk between 0 to L, and you ask that what is the average time it takes to reach either of these two boundaries, the maximum time it would take is if you were starting at the middle. If you were starting at closer to any one of the boundaries, you would have, see, maybe it's not immediately obvious because you would have shorter paths, but you would also have longer paths. But it works out that the maximum time that you would take where both paths are sort of equally weighted is when you're in the middle of the lattice. Okay, so when x naught is L by 2, and this is the sort of A that it follows. On the other hand, for example, if you were to say that, well, my one end is reflecting and the other end is absorbing. So, for example, if you were to say that, let us say this left end is absorbing, so mean time from 0 is 0, and this right end is reflecting, which means that del tau of x del x at x equal to L is 0. Okay. So, if you put in this boundary condition that this is absorbing, that is reflecting, then of course, and if you plotted this curve again between 0 to L, the maximum time it would take if your particle had started at L, because that is my reflecting condition, and you would get something like this, and that expression would be tau of x naught is 1 by 2d 2 Lx minus 2 Lx minus x square. Okay. So, when x naught is equal to L, you start at the other boundary, that is the maximum time, and then of course, if you start at the left boundary, the time is 0. Because essentially, remember, when I say I have a reflecting boundary condition, it means that your particle comes here, it gets reflected back, it goes back out, which means what? Which means that the current over here is 0, because whatever comes in comes out. Current is what? Del del x, the first derivative. So, that current is 0. So, that amounts to this boundary condition. Okay. All right. And again, so this mean, for example, is this sort of mean time is, again, this is of course, you can I worked it out for 1D, but you can generalize it to any dimensions. And again, just like you would expect from the diffusion equation, the generalization is that the Laplacian of this mean time is equal to minus 1 by d. Instead of just del 2 del x2, it's just the Laplacian is equal to minus 1 by d. All right. I just wanted to do this sort of, so this is a derivation essentially for this sort of special, because for the simple random walk, I can just write this down, this recursion relation. But there's a way to do this more formally, starting with the distribution of first passage times and calculating moments systematically. So that's what we'll do. But it's good to have this in at the background, so that whatever complicated things we do, we can check that at the end of the day, if I'm talking of simple processes like this, I get back to this equation for the mean first passage times. Okay. Questions? Absorbing boundary condition, and this is a reflecting boundary condition. See, generally, of course, when one is talking about the stochastic processes, we talk about this forward probabilities, and we talk about, for example, MSDs and so on. So those are the transport properties, but this times of passage is another very important thing that is also in biological context very important, because biological processes need to regulate times in a sensitive fashion as well. So we'll discuss some biological examples, of course. So one more day maybe for the formalism, and then we'll discuss for some examples. Okay. All right. So I'll stop here for today.